welcome back. The specific objectives of this particular lecture are to present expressions for overall heat transfer coefficient, present expressions for various heat transfer areas in plate fin type air cooled condensers, present typical correlations for heat transfer coefficients on air side, water side and condensation heat transfer coefficient, and discuss effects of non-condensible gases. At the end of the lecture, you should be able to estimate the overall heat transfer coefficient values for heat exchangers with and without fins, calculate various heat transfer areas in plate fin type air cooled condensers, use various correlations and estimate heat transfer coefficients on external fluid side and on condensing refrigerant side, and discuss effects of non-condensible gases. So, let me give a let us look at a typical design problem. Normally in any design problem the inputs are the operating temperatures, that means the evaporator temperature, condenser temperature, etc., refrigeration capacity QE, the heat rejection ratio HRR, mass flow rate and inlet temperature of external fluid, that is M external, and T subscript external I. Okay, normally these values are available in any typical design problem. And what is the objective of the design problem? Objective is to find out the area required, that is we have to find out A, and the equations available are like this. First equation is like we have seen in the last class that the heat rejection rate in the condenser QC is given by QC is equal to heat rejection ratio HRR into refrigeration capacity QE. So, we know both HRR as well as QE because they are given as input. So, from this equation we can calculate what is the total heat transfer rate at the condenser. Okay, so, this is the first equation one should use. We can also write the heat rejection rate at the condenser in terms of the external fluid. That means we can write QC is equal to MCP of external fluid into T external out minus T external in, right. In this equation we you can see that we know M external, that means the mass flow rate of the external fluid is known to us and the inlet temperature of the external fluid is known to us. So, from this we can calculate what is the outlet temperature of the external fluid since QC is known to us. The third equation that we will be using is the expression for log mean temperature difference. This is defined in the last lecture. This is defined in terms of the fluid inlet and outlet temperatures and the condensing temperature. Since we know all these temperatures, we can calculate what is the log mean temperature difference. Finally, what we do is we use this equation, that is QC is equal to U into A into LMTD. In this equation QC is known to us, LMTD is known to us, and we have to find out A. So, for what we have to do is we have to somehow estimate the overall heat transfer coefficient U. So, that using this one equation we can calculate what is the area required, right. So, this is the general procedure to be followed in the design of any heat exchangers, not necessarily the condenser. Okay, from the given input we have to find out the mean temperature difference, and then we have to find out what is the overall heat transfer coefficient. Okay, once we know the overall heat transfer coefficient, then we can find out the area required. These kind of problems are known as design problems. Okay, so the objective is to find or design the heat exchanger or to find out the area required. There are other types of problems known as rating problems in which the area is given. Okay, and we have to find out what is the heat transfer rate. Okay, so in this particular lecture I am confining myself to the design problem, typical design problem, how to estimate the area. Okay. So, first as I have already mentioned, in order to estimate the area we have to first find out what is the overall heat transfer coefficient U. So, evaluation of U is an important step in the design of a condenser. The overall heat transfer coefficient can be based either on internal area AI or external area AO of the condenser. Okay, and in general we can write the product UA, that is equal to UIAI, which is equal to UOAO, which is nothing but 1 by summation of Ri, okay, from I is 1 to n, where Ri is nothing but the heat transfer resistance of the ith component. Okay. Now, a general expression for overall heat transfer coefficient of a finned heat exchanger is given by this expression. As I have already explained to you, this is the overall heat transfer coefficient, that means UA. Okay. This depends upon your different resistances which are in series. So, for any general heat exchanger there are 5 resistances here. Okay. For example, the first resistance, this resistance accounts for the convective resistance of the outer surface. That means that is why the subscript O is there, okay, of a finned heat exchanger. So, this is the convective heat transfer resistance of the outer finned surface, that is resistance 1. Then you have second resistance, this is nothing but the conductive resistance offered by the wall of the heat exchanger or wall of the condenser. Then the third resistance, this one is nothing but the convective resistance offered by the inner finned surface, okay. Then we also can have the resistance due to fouling on the outer surface and resistance due to fouling or scale deposition on the inner surface. So, we have 5 resistances, okay, 1, 2, 3, 4, 5. These 5 resistances are in series. So, in order to calculate the overall heat transfer coefficient, we have to add up the all these resistances and we have to inverse it. Okay. So, in the above equation, the nomenclature is given here. H stands for the convective heat transfer coefficient, A subscript F and A subscript B stand for finned and bare tube surface areas, eta subscript F stands for the fin efficiency, delta X is the thickness of the wall, K subscript W and A subscript M stand for thermal conductivity and mean area of the wall, and R subscript F is the fouling factor, and subscript I and O stand for inner and outer sides. Now, let us look at some special cases where some simplification is possible. For example, for an air cooled condenser with fins only on air side, that means we do not have any fins on the internal side, okay. And for this kind of a condenser, you find that the fouling on fin side is small compared to the convective heat transfer resistance on the fin side. So, we can neglect the resistance due to fouling on the fin side. If you neglect resistance due to fouling on the fin side, you find that the expression for overall heat transfer coefficient is given by this equation. Okay, so, this is obtained by simplifying the equation shown in the previous slide. Okay. So, here we have this term accounts for the internal convective resistance, this term accounts for the resistance due to fouling on the internal side, and this accounts for the conductive resistance of a cylindrical wall. Okay. Here Kw is the thermal conductivity, Ro and Ri are the outer and inner radii of the tube. Okay. And finally, this one, this accounts for the external or outer convective heat transfer resistance. Since there are fins on the outside, we have to have the finned area and the fin efficiency. Okay. And here A naught is nothing but the total area, which is equal to A fin plus A bare. Okay. And for water cooled condensers without fins, further simplifications are possible. Since there are no fins either on the outside or inside, you do not find any fin efficiency or fin area. Okay. And for water cooled condensers, in which the water flows through the tubes, the fouling on the outer side, that means where the refrigerant flows, is generally negligible. Okay. So, you do not find any fouling resistance on the refrigerant side. So, you have the internal convective resistance, that means on the water side, and this is the fouling resistance on the water side, and this is the resistance offered by the wall, and this is the refrigerant side, the convective resistance. Okay. So, the equation becomes simplified. Right. So, depending upon the particular case and starting with the general expression for the overall heat transfer coefficient, you can simplify it to a particular case. Okay. Of course, you can also do the design for a heat exchanger where fins are there on both outside as well as inside, and fouling is there on both out as well as inside. Okay. And I was mentioning that for water cooled condensers without fins. Okay. Generally, in a water cooled condenser, the water side heat transfer coefficient will be quite large. Okay. And if you are using ammonia as a refrigerant, then you get very high heat transfer coefficient on the refrigerant side also. So, you find that for ammonia based water cooled condensers, the heat transfer coefficient on refrigerant side as well as on the water side both are large. So, you need not use fins. Okay. But if you are using water cooled condensers with CFC refrigerants or fluorocarbon based refrigerants, we find that the heat transfer coefficient on the refrigerant side is much smaller compared to the heat transfer coefficient on the water side. Okay. In such cases, it may be necessary to use fins on the refrigerant side. Okay. So, that is what is generally done in practice. So, whenever fluorocarbons are used in water cooled condensers, the tubes on the refrigerant side are made integrally finned. Okay, so that you can enhance the heat transfer on the refrigerant side. Okay. In such case, you have to consider the fin effectiveness and the fin area on the refrigerant side, right. Now let us look at fin efficiency. In fin heat exchangers we have to find fin efficiency. Fin efficiency depends on the type and material of the fin and on fluid flow characteristics. Expressions for fin efficiency can be derived analytically for simple geometries. However, for complex geometries the fin efficiency has to be obtained from actual measurements and manufacturers' catalogs. The most commonly used fin configuration, as I have already discussed in the last class also, is the plate fin type, which is approximated with an annular fin. So let us see how the approximation is done. As you know, this is the plate fin type of the condenser, where you have the tubes, okay, through which the refrigerant flows, and you have the plate fins on the outside over which the air flows, and this is the side view of the heat exchanger. Okay. Now, analytical expression for fin efficiency of this kind of heat exchanger is difficult. Okay. So, what is done is this is equated to an annular fin, that means this is an annular fin for which analytical expressions are available. So, what is done is first the entire fin area is equally distributed among all the tubes. For example, if you look at this picture, here there are 12 tubes. Okay. So, the entire fin area is equally distributed among the 12 tubes. Then one particular plate fin segment is considered. That particular plate fin segment looks like this. You have a single tube and the area associated with a single tube. Okay. And this is equated to an annular fin. And how how this is done? This is done by equating the fin areas. Okay. That means what is done is simply this area is equated to this area. Okay. And by equating these two areas, the outer radius of this annular fin is obtained, and then using the analytical expression for the annular fin, the efficiency of the plate fin is obtained. Okay. So, let me quickly show the equations. So, the area of a single fin, if you look at the earlier picture, is given by B into C minus pi r1 square, where B and C are the breadth and height of the rectangular fin, and r1 is the inner radius of the annular fin. Okay. So, you have the annular fin like this. So, this is r1 and this is r2. Okay. R2 is not known to us. Now, what is done is this area is equated to the area of the annular fin. Okay. So, the area of the annular fin is nothing but pi into r2 square minus r1 square. So, this should be equal to B into C minus pi r1 square, and B and C are known to us and r1 is also known to us. So, by equating these two expressions, we get an expressions for r2, and r2 is simply equal to square root of B into C by pi. Okay. So, we can find out the outer radius of an equivalent annular fin. Okay. Then the efficiency of the rectangular fin is obtained from the efficiency of an equivalent annular fin having an inner radius of r1 and outer radius of r2, which is equal to square root of B into C by pi. Okay. So, this is the procedure generally followed, and this picture here shows the fin efficiency of an annular fin. Okay. So, here we have on the y axis the efficiency, on the x axis we have this parameter r naught minus ri into h naught divided by kt to the power of 1 by 2. Okay. And this is plotted for different r naught by ri ratios, and this is obtained analytically. Okay. And in this expression in the x axis, the h naught is the convective heat transfer coefficient on the fin surface, k is the thermal conductivity of the fin material, and T is the thickness of the fin. Okay. So, we get this kind of charts are available. So, we can find out if you know R naught and Ri and the thermal conductivity and thickness and heat transfer coefficient, you can find out the fin efficiency. Okay. So, this is how the fin efficiency of plate fin is obtained. Now, let us look at plate fin and tube type air cooled condensers, and let us look at various areas of heat transfer. Okay, first let us see what how this is constructed. In this type of heat exchangers, as we have already discussed, air flows through the passages formed by the fins, and heat transfer takes place from fins and the exposed part of the tube. Hence, heat transfer occurs from the following areas. Heat transfer takes place from the bare tube area between consecutive fins, and this area is called as A subscript B, and heat transfer also takes place from the area of the fins A subscript F. And these areas are expressed in terms of per meter square of face area and per row. Okay, so the units of for our example, the units are meter square per meter square of face area per row. Now, what is the face area? Face area is the area of condenser seen from outside. Okay, that means this is the plate fin type of condenser. So, this is how you see it from outside. Okay, so the face area is nothing but this area. Okay, if this is the width and this is the height. Okay, this entire thing is the height and this is the width, then face area is W into H. Okay, but you will find from this figure that the actual area available for airflow is not equal to face area, because the actual area available if we look at this drawing is nothing but this. Okay, because face area consists of the area occupied by the fins as well as the area occupied by the tubes. Okay, so this area minus the area occupied by the fins minus the area occupied by the tubes is what is available for the flow rate of the air. Okay. So, the actual flow area is less than the face area since fins have finite thickness, as I have already explained. Further, air has to flow through the narrow passages between the tubes, and the flow area is minimum at these locations, and this minimum area is denoted by A subscript C. To find the various areas, we consider a condenser of 1 meter height and 1 meter width. That means we take a condenser having a face area of 1 meter square, and all the dimensions are expressed in millimeters. And we will use the following nomenclature. B is the vertical spacing between tubes in a row. That means this is one single row. So, B is this. Okay, center to center distance between two adjacent tubes. And C is the spacing between tubes in different rows. That means in the side view, this is the center to the center distance between two adjacent rows. Okay, that is C. And T is the thickness of the fin. Okay, this is T. And D is the center to center spacing between the fins, that is this, and D naught is the outer diameter of the tube. Okay, that means this is D naught, and Di is the inner diameter of the tube, that means this. Okay, so this is the nomenclature we use. Now, number of tubes per meter height is nothing but 1000 divided by B. We are using 1000 because B is in millimeters. Okay, so number of tubes per meter height is 1000 by B, and these are the number of tubes per meter square face area per row. Next, number of fin passages per meter width. This is given by 1000 by D, and these are the number of fin passages per meter square face area per row. And the number of fins per meter square face area is nothing but 1 plus 1000 by D, which can be approximated as 1000 by D. Okay, because the D is generally small. And width of each passage is nothing but capital D minus T by 1000, because capital D is the center to center distance between two adjacent fins, and small t is the thickness of a fin. Now, then the various areas are as follows. The bare tube area, okay, A subscript B is given by tube perimeter into number of fin passages into number of tubes into width of each passage. Okay. So, bare tube area is basically nothing but this area. Okay. So, excluding the fins. Like this you have to account for all the tubes in a row per meter square of face area. Okay. So, if you substitute the expressions for tube perimeter which is nothing but pi d O divided by 1000, and number of fin passages are 1000 per divided by D, number of tubes is 1000 divided by B, and width of each passage is D minus T by 1000. So, if you substitute all this, finally you find that the bare tube area is given by D minus T divided by dB into pi D, and this is a meter square per meter square face area per row. Okay. Likewise, we can calculate other areas, for example, the fin area. Okay. Fin area means, for example, you look at one fin, a single fin. For a single fin, the fin area is nothing but this area excluding the area occupied by the tubes. Okay. You have to multiply this by 2 because heat transfer is taking place from both sides of the fin. This is the area of a single fin. So, like that you have to find out how many fins are there per meter square of face area. Okay. So, if you substitute the expressions, you will find that the fin area is given by A subscript fin is equal to 2 by capital D into C minus pi d o square divided by 4b. Similarly, the minimum flow area is actually between the tubes, and the minimum flow area is somewhere here. Okay. So, this is where the passage becomes narrow, okay, and this distance is the minimum distance. So, we can find out what is the flow area at this point. Okay. So, the expression for that is given by this A subscript C is equal to capital D minus T by D into 1 minus D O by B. Okay, and the total heat transfer area A subscript O is bare tube area plus fin area, that is AB plus AF. So, if you know all these parameters like C, capital D, small do, B, etc., you can calculate all these areas per meter square face area per row. Okay. Next, we find the wetted perimeter. Wetted perimeter P is defined as total heat transfer area divided by length in flow direction. Length in flow direction is nothing but per row, it is nothing but C divided by 1000. So, wetted perimeter is A subscript O, that is the total area divided by C by 1000. Okay. Why do we need wetted perimeter? Because the hydraulic diameter is defined as 4 into minimum flow area, that is A subscript C divided by wetted perimeter. Okay. Hydraulic diameter is defined in terms of wetted perimeter and minimum flow area. So, if you substitute the expression, you find that the hydraulic diameter is given by 4 into C into A subscript C divided by 1000 A subscript O. Okay. And why do we need hydraulic diameter? Because the Reynolds number and the Nusselt number are based upon hydraulic diameter. So, if you want to find out the Reynolds and Nusselt number, because the heat transfer coefficient depend on these numbers, we have to find out the hydraulic diameter. Okay. And the inside heat transfer area A subscript I is nothing but pi di by 1000 into number of tubes. So, this simply becomes pi di divided by capital B. Okay. So, this is how we can estimate if you know the center to center spacing between the tubes, fins, fin thickness, etc. per meter square per row, we can estimate different areas, okay, heat transfer areas, and we can also estimate the hydraulic diameter, which will be used in estimating the heat transfer coefficients. Okay. Now, let us look at how to estimate heat transfer coefficients on the external fluid side as well as on the refrigerant side. Okay. First, let us look at heat transfer coefficient on the external fluid side. First, let us look at air cooled condensers. So, air side heat transfer coefficient in air cooled condensers. For flow over fin surfaces, okay. So, that means we will be obtaining heat transfer coefficient for air flow over fin surface. So, correlations have been obtained by Case and London for various fin and tube configurations for both inline as well as staggered arrangements. Okay. So, what is inline and staggered arrangements? This is tubes in line. Okay. So, you can see that tubes in adjacent rows, they are in line. Okay. So, this is inline arrangement, whereas here the adjacent tubes are not in line. Okay. So, you call this as staggered arrangement. Okay. So, Case and London have obtained expressions for heat transfer coefficient for both these arrangements, that means for inline as well as staggered arrangements, and they have found a general correlation that is given by Nusselt number is equal to 0.117, Reynolds number to the power of 0.65, Prandtl number to the power of 1 by 3. And remember that here the Nusselt and Reynolds number are based on hydraulic diameter. So, once you know the hydraulic diameter and velocities, etc., you can calculate the Reynolds number, Prandtl number, from that you can calculate the Nusselt number, and from the Nusselt number you can calculate the heat transfer coefficient. Now, there is another simple expression proposed by Air Conditioning and Refrigeration Institute, Arlington, the USA, that is simply it relates heat transfer coefficient to the phase velocity. Okay, that is given by H naught is equal to 38 into V to the power of 0.5, where V subscript F is the phase velocity in meter per second, and H naught is the heat transfer coefficient in watt per meter square Kelvin. Okay, so in the absence of detailed data, you can use this simple expression for rough estimation of heat transfer coefficient on fin surfaces. Okay. Then pressure drop on air side for fin surfaces, Rich has proposed the following correlation. Here the correlation is it correlates pressure drop in pascals per row in terms of number of fins per meter and the phase velocity V. Okay. So, this is the correlation delta P in pascals per row. This is an empirical correlation. So, this is equal to 7.15 V to the power of 1.56 if number of fins are 315 per meter. Similarly, this is the expression for number of fins of 394 per meter, 472 fins per meter, this is the expression, 531 fins per meter, this is the expression, and here again V is the phase velocity. Okay. So, this is again a simple empirical correlation based on experimental observations. Now, let us look at flow over tube banks. For flow over tube banks, Grimson has proposed correlation, and the correlations are based on maximum velocity V max. V max is where the area is minimum. Okay. So, V max is nothing but Vf into B divided by B minus D naught, where V subscript F is the phase velocity. B, as you have seen, is nothing but the center to center distance between tubes in a particular row, and D naught is the outer diameter of the tube. So, the expression is like this: Nu is equal to C into Re to the power of n into Pr to the power of 1 by 3, where Re is the Reynolds number and Pr is the Prandtl number. And the Reynolds and Nusselt numbers are defined like this: rho into V max. Okay. So, here the Reynolds, you have to be very careful how the Reynolds number and Nusselt numbers are defined. Okay. So, here it is defined in a slightly different manner. Here we are not using hydraulic diameter or anything, but simply we are using the outer diameter of the tube, because we are talking about tube banks. Okay. So, D naught is the outer diameter of the tube, mu is the viscosity of air, rho is the density of air, and V subscript max is the maximum velocity given by the above expression. Similarly, Nusselt number is given by H into D naught divided by K, where K is the thermal conductivity of air, H is the convective heat transfer coefficient. So, first find out Reynolds number and Prandtl number, and then find out Nusselt number, and from that find out the heat transfer coefficient. And the constants C and N are dependent on Reynolds number. For example, these constants are given in this table. If the Reynolds number is between 0.4 to 4, then the constant C is 0.989 and constant N is 0.33, and if it is between 4 to 40, the constant C is 0.911 and the constant N is 0.385. Like that, for different Reynolds number covering a wide range, the different values of constant C and N are given. Okay. So, we can use this table and get the values of C and N, then use the correlation and find out the heat transfer coefficient. And correlations for pressure drop for airflow over tube banks. Okay, we have seen the pressure drop correlation for fin surfaces. So, now the pressure drop correlation for tube banks is given by this expression. It is given suggested by Pearson and Hughes, and here delta P is given by Fn V square by 2, where F is the friction factor and N is the number of rows. Okay, so, you can see that the pressure drop depends upon the number of rows. And V is the velocity, and the friction factor F is given by this expression: F is equal to Reynolds number to the power of, for tubes in line, okay, in line arrangement, this is the expression, F is equal to Re to the power of minus 0.15 multiplied by 0.176 plus 0.32 B divided by A minus 1 to the power of 0.43 plus 1.13 by B. Similarly, for staggered tube arrangement, this is the expression for friction factor. Okay. So, if you know the number of rows and if you know the velocity, and if you then you can calculate the friction factor and delta P. And in this friction factor expression, the constants A and B are defined in terms of the tube to tube spacing capital B and the outer diameter of the tube D naught, and row to row spacing C. Okay. So, if you know these details, we can find out A and B, then from that we can find out the friction factor. Okay. Now, for this is whatever expression we have shown so far hold good for forced convection type air cooled condensers. Okay. So, in fact, in the last lecture I have also mentioned natural convection type condensers. Okay. One thing I would like to emphasize here is that the correlations I am showing are not the only correlations. Okay. If you look at heat transfer or fluid mechanics literature, a large number of correlations have been developed over the years. Okay. The correlations vary and they are applicable for some particular ranges, and some correlations are more accurate than other correlations, right. So, huge amount of literature is available, and one has to choose the right correlation and use the correlation and obtain the heat transfer coefficient and pressure drop values. Okay. So, for example, for free convection over hot vertical flat plates and cylinders, a typical correlation is given here. The average Nusselt number NuL. Okay. Here L is the height of the plate or height of the cylinder, and Nu is the average Nusselt number. This is defined as average heat transfer coefficient multiplied by the height of the plate or cylinder divided by the thermal conductivity of air. Okay. That is equal to C into Gr subscript L into Pr to the power of n, where Gr is the Grashof number, Pr is the Prandtl number, and the product of Grashof and Prandtl number is called as another is Rayleigh number, okay, Ra. And here the subscript L means the characteristic length should be L, that is the height of the plate, right. So, here again you can see that there are constants C and N, and the values of C and N depend on the value of Rayleigh number. So, just like the earlier expression where we had values for C and N for different Reynolds number, for this particular case also the values of C and N for different values of Rayleigh number have been obtained and they are tabulated. So, we can find these values if you know the Rayleigh number, right. And correlations for other conditions are also available in literature, for example, for horizontal flat plate or horizontal cylinders, etc. Okay. So, what I am showing is just an example of a typical example of heat transfer coefficient correlations. Now, let us look at water cooled condensers and see how to calculate water side heat transfer coefficients in water cooled condensers. Normally, we have seen that water flows through the tubes, and generally that flow is turbulent. So, if the flow is turbulent and if the flow is through the tubes, then we can use a simple Dittus-Boelter correlation which was discussed earlier. The Dittus-Boelter correlation is very popular and it is given by this expression Nu subscript D, this is a Nusselt number based on the inner diameter of the tube. This is equal to 0.023 into Reynolds number to the power of 0.8 and Prandtl number to the power of 0.4. Okay, this is for turbulent flow inside the tubes, right. And as I said, Re is the Reynolds number and Pr is the Prandtl number, and this Re, that is Reynolds number and Nusselt number, are based on the internal diameter of the tube. This can be used most of the time, but if viscosity variation is large, then one can use Cedar-Tate equation which gives better accuracy. Okay, so this Cedar-Tate correlation is given by this Nu subscript D is equal to 0.036 Re to the power of 0.8 Pr to the power of 1 by 3 multiplied by mu W to the power of 0.14. Here mu W is nothing but the viscosity of water at wall temperature, and this is the viscosity of the water at bulk temperature. Okay, so this expression can be used if the temperature variation between the wall and bulk fluid is large, or if the viscosity variation is large. Okay, and correlations are also available for laminar flow through tubes, both for developed and developing flows. Now, let us look at condensation heat transfer coefficient. Condensation can be in general film wise or drop wise. Okay, as the name implies, film wise condensation means the entire surface will be covered with a film of refrigerant. Okay, that means the liquid film of refrigerant covers the entire surface of the condenser tube. Okay, so or a plate. So that kind of condensation is known as film wise condensation. Drop wise condensation means the liquid does not cover the entire surface, but there are areas where liquid is present and there are areas where liquid is not present. Basically, condensation takes place in the form of droplets. Okay, so that is known as drop wise condensation. Generally, we find that whether the condensation is film wise or drop wise depends upon several factors. Okay, one of the important factors which decides whether the condensation is film wise or drop wise is the nature of the surface on which condensation is taking place. Okay, and generally the drop wise condensation gives much higher heat transfer coefficient compared to film wise condensation. Okay, so surfaces can be treated so that we can have drop wise condensation on the surfaces. Okay, but in heat transfer literature and in the design of condensers, normally we assume that the condensation is film wise condensation. Okay, this is because even though you have drop wise condensation in the beginning, after prolonged use the surface may lose its characteristics and slowly the drop wise condensation may give rise to film wise condensation. So, if you have designed it the condenser based on drop wise condensation, then you find that after some time the condensation becomes film wise condensation and the heat transfer coefficient will be less. Okay. There that means after prolonged use the capacity of the condenser reduces because the heat transfer coefficient reduces. Okay. So, to avoid this one, all the condensers are designed based on assuming that the condensation is film wise condensation. Okay. So, this is a conservative approach because the area that you obtain using this assumption is conservative, that means you are under predicting the heat transfer coefficient. Okay. As I said, normally design calculations are based on film wise condensation. The condensed liquid film resists heat transfer, hence for high heat transfer rates liquid film should be as thin as possible. So, let me quickly explain this with a very simple example. For example, we have a plate, let us say. Okay, this is plate, plate let us say for the time being is a horizontal plate, this is in contact with a vapor. Okay. Let us say that this vapor has a saturation temperature of Tsat, okay, at that particular pressure P, and let the surface be at a temperature T which is less than Tsat, right. So, when this vapor comes in contact with a surface, this surface whose temperature is less than the saturation temperature of the vapor, then this vapor condenses on the surface and rejects the heat of condensation to this particular surface. Okay. That means you will find that this surface will be gradually covered with a layer. Okay. If you are assuming film wise condensation, you will find that this surface is covered by a liquid film. Okay. Once a liquid film is formed on the surface, this liquid film will add resistance for heat transfer. That means this itself prevents or reduces the rate at which heat is being transferred from vapor to the surface. Okay. That means additional resistance is created because of the presence of the liquid film. Now, how effective is this condensation process depends upon what is the thickness of the liquid film. Now, if you have a horizontal surface, then this liquid film may grow in thickness. So, you will find that the condensation rate reduces progressively. But suppose you have a vertical surface, let us say, or a vertical cylinder, and if condensation is taking place on the outside, then because of the gravity the liquid film will continuously drain out. So, you will find that the condensation rate will be high. Okay. So, basically the condensation heat transfer coefficient depends upon how you have oriented the surface and how fast the condensate is being drained out. Okay. So, this is an important factor to be considered in the design of condensers. So, as I said, for good design a continuous draining of condenser liquid is required, and this depends mainly on the geometry of the condensing surface. Now, let us look at a simple case where condensation is taking place outside horizontal tubes. Okay, that means you have a so you have a tube like this, let us say, and inside the tube the coolant is flowing. Okay, this is coolant, and outside you have the refrigerant vapor. Okay. So, when the refrigerant vapor comes in contact with this tube, outside the tube condensation occurs. So, a film of liquid film of refrigerant forms on the outside of the horizontal tube. Okay. For such cases, Nusselt has given a correlation. This is a classical correlation suggested by Nusselt. Here in this particular correlation, H naught is the condensation heat transfer coefficient. Okay. And here Kf, this is the thermal conductivity of the saturated liquid refrigerant, and rho f is the saturated density of the liquid refrigerant, and rho g is the saturated density of the vapor, g is the acceleration due to gravity, hfg is the latent heat of vaporization, n is number of tubes in a row, okay, in a vertical row. That means in a vertical row if there are 3 tubes, then n becomes 3, and d naught is the outer diameter of the tube, mu f is the saturated viscosity of the liquid, and delta T is the temperature difference between the surface and the saturated refrigerant. Okay. So, delta T is T refrigerant minus, okay, so this is T saturated minus T wall, right. Since the density of the liquid is much larger than the density of the vapor, so we can neglect this term, okay. Then this Nusselt's correlation simplifies to this form, okay. H naught is 0.725 multiplied by this factor to the power of 1 by 4. Okay. This expression has been obtained analytically assuming that the vapor is still. Okay. That means the vapor is not moving, you have a condensing surface in a still vapor. Okay. But in actual case you find that there will be some vapor movement. Okay. That means the correlation suggested by Nusselt will always result in is a conservative correlation, because the heat transfer coefficient obtained by using this will be slightly smaller than the actual condensation heat transfer coefficient because of the movement of the vapor. Okay. And here all the properties, that is the thermal conductivities, densities, latent heat, viscosity, etc., are evaluated at mean film temperature. Okay. Mean film temperature is defined as the saturation temperature of the vapor plus wall temperature divided by 2. Okay. So, this is the condensation heat transfer coefficient outside horizontal tube. Again Nusselt has suggested an analytical expression for condensation outside vertical tubes. Okay. So, this also looks similar in form to the earlier expression. Okay, again the nomenclature is same, this is the thermal conductivity of saturated liquid. Here F stands for saturated liquid and G stands for saturated vapor. Okay. And here L is the height of the vertical tube, and again delta T is the temperature difference, G is the acceleration due to gravity, HFG is the latent heat of vaporization. If you compare a horizontal and vertical tube and the expressions, you find that the heat transfer coefficient for a vertical tube, if everything else is remaining constant, will be larger compared to a horizontal tube, because condensate can drain out better in case of a vertical surface. Okay. So, you get a higher heat transfer coefficient here, and this above expression is valid for laminar flow, that means up to Reynolds number of 1800, and the Reynolds number here is defined as REF. This is the Reynolds number expression. REF is 4 into m subscript f divided by pi mu f into d, where m subscript f is the condensation rate and mu f is the viscosity of the saturated liquid and d is the outer diameter of the tube. And in terms of condensation number CO, Kirkbride has suggested this correlation. This is Kirkbride's correlation for condensation on vertical tubes outside the vertical tube. So, here this H naught is the heat transfer coefficient obtained from Nusselt's expression. Okay. And again mu f is the viscosity and rho f is the density, Z is the acceleration due to gravity, and Kf is the thermal conductivity. So, here this entire quantity is known as condensation number. Condensation number is equated to Reynolds number, right, REF. So, condensation number is 1.514 into Reynolds number to the power of minus 1 by 3. So, this is the Kirkbride's correlation. Kirkbride has also suggested a correlation for turbulent flow, that means when the film Reynolds number is greater than 1800. Okay. So, if the film Reynolds number is greater than 1800, then the condensation number defined by this parameter is equal to 0.077 into REF to the power of 0.4. Okay, where H naught is the condensation heat transfer coefficient, mu f is the thermal conductivity and all. So, if you know the film Reynolds number and if you know the properties, then you can calculate the condensation number, and from the condensation number you can calculate what is the heat transfer coefficient. Okay. Similarly, in the previous this thing, in the previous expression for laminar flow also, if you can find out the film Reynolds number, then you can calculate the condensation number, and from the condensation number and the properties you can calculate what is the external heat transfer coefficient. Now, let us look at condensation inside tubes. This is more complicated actually, okay, compared to condensation outside the tubes or outside the surface. This is because condensation inside tube causes a reduction in the area of condensation due to liquid collecting at the bottom of the tubes. That means, let us say that refrigerant vapor is flowing through the tube. Let us say take a large tube. Okay. This is the wall of the tube, and outside you have coolant. and refrigerant is flowing through the tube. When refrigerant is flowing through the tube, since the coolant is flowing outside, refrigerant starts condensing on the surface of the inner surface of the tube. When it condenses in the inner surface of the tube, the liquid, because of the gravity, will come down, and you may find that liquid is settling down at the bottom. Okay, when liquid is settling down at the bottom, the resistance at the bottom is different from the resistance at the top, right? And the heat transfer area, effective heat transfer area available for heat transfer, is also gets reduced because of the liquid collection at the bottom of the tube. Okay, so this factor has got to be considered while estimating the condensation inside heat transfer coefficient inside the tubes. And the draining of the condensate may retard or accelerate the vapor flow depending upon whether the condensate flows in the same direction as the vapor or in opposite direction. That means when the condensate and vapor are flowing in the same direction, then the vapor flow gets accelerated, whereas if they are flowing in the opposite direction, the vapor flow gets retarded, and this also has an effect on the heat transfer coefficient. Hence, flow rate of vapor has considerable influence on the heat transfer coefficient. A large number of correlations have been developed for a variety of flow conditions, and I will show you here one of the simplest correlations. This is suggested by Chadok and Chato. This is known as Chadok and Chato correlation. Here the correlation is like this: H subscript Tp is nothing but the condensation heat transfer coefficient inside the tube. Okay, this one. This is equated to H naught, where H naught is the heat transfer coefficient for condensation outside the tubes. Okay, that means you can use Nusselt's correlation or Kirkbride's correlation and estimate H naught, which is nothing but the condensation heat transfer coefficient outside the tubes. Then condensation heat transfer coefficient inside the tube is equal to 0.77 multiplied by H naught. Okay, and if you substitute the expression for H naught, the Chadok and Chato correlation is like this: heat transfer coefficient inside the tubes. Okay, so is 0.555 multiplied by this factor. Okay, so this is similar to your Nusselt's correlation, with the difference that instead of latent heat of vaporization, here what is used is a modified enthalpy of evaporation is used in Chadok and Chato correlation. That is defined by this. The modified enthalpy of evaporation H subscript Fg, okay, H prime subscript Fg is equal to HFg, which is nothing but the latent heat of vaporization, plus 3 Cpf, where Cpf is the saturated specific heat of the liquid, multiplied by T refrigerant minus T vol divided by 8. Okay, so you have to first find out this, then you substitute this in this, then find out the heat transfer condensation heat transfer coefficient inside the tubes. Okay, so this is one of the simplest correlation available for heat transfer coefficient inside the tubes. As I said, this is a very complicated case, and the heat transfer coefficient value will be varying depending upon the flow regime, okay, or flow pattern. For example, if the tube is vertical, you have one heat transfer coefficient. If it is horizontal, you will have another heat transfer coefficient. If it is inclined, you will have a different heat transfer coefficient. So, depending upon the geometry, depending upon the flow rates and all, the heat transfer coefficient will be different. Okay. And a large amount of literature is available for estimating condensation heat transfer coefficient for different types of geometries, different flow rates, etc. Okay. Now, let us look at the other factors. I was discussing about the fouling factor. Okay, generally the fouling takes place when we are using water cooled condensers, because on air side the fouling is generally less. So, whenever we are using water cooled condensers, normally fouling occurs on the water side. Okay, and the condenser tubes are clean when they are new. Okay, so the overall heat transfer coefficient will be high when it is new, but with usage some scale formation takes place. Scale formation can take place both on water side as well as on refrigerant side, but most of the time the scale formation is mainly on the water side. And as a result of the scale formation, additional resistance to heat transfer is created, and because of this the value of overall heat transfer coefficient decreases. So, we have to know what is this fouling factor, and what is done generally is at the time of design itself, even though new tubes do not have any scale formation, we take account of the fouling factor and use some fouling factor and estimate the overall heat transfer coefficient. And Stoker has suggested the following values for fouling factors. For example, the fouling factor is 0.00009 meter square Kelvin per watt for fluorocarbon based refrigerants with copper tubes, and the fouling factor is 0.000178 meter square Kelvin per watt for steel tubes with ammonia. Okay. And periodic descaling is required to control fouling. Okay. So, from time to time you have to shut down the plant and clean the tubes. And now let us look at effects of air and other non-condensables. This is usually a problem with high boiling point refrigerants such as R11 and R113, which operate under vacuum, leading to air leakage into the system. In addition, some air may be left behind at the time of system evacuation and charging. Okay, so because of these two reasons, in addition to refrigerant, you will also find some air or other non-condensable gases inside the system. And if some non-condensable gases or air enters the system, they will finally collect in the condenser. And what is the effect of these non-condensable gases which get collected in the condensers? The first effect is that the total pressure in the condenser will be higher than the saturation pressure at condensing temperature. That means the total pressure is equal to P saturated at the condensing temperature, that is P ref plus P non-condense. That means here in this expression, this is the total pressure and this is the partial pressure of the refrigerant and this is the partial pressure of the non-condensable gases. So, you find that the total pressure increases. Total pressure increases means the discharge pressure of the compressor has to increase. Not only this, you also have a second effect, that is the non-condensable gases cling to the condensing surface, increasing the resistance to heat transfer. Okay. Hence condensing temperature increases, right. So, because of these two factors, we find that there is an increased compressor discharge pressure. That means whenever there are non-condensable gases, the condensing temperature increases and the discharge pressure also increases. Once the discharge pressure increases, the compressor power input has to increase for the same mass flow rate. Okay. So, ultimately the COP of the system reduces. So, we have to make sure or we have to maintain the concentration of the non-condensable gases below a certain acceptable level. Okay. If it increases, then we may have to stop the plant and purge the plant of all these non-condensable gases and air. Okay. Now, let us quickly look at the existence of an optimum condenser pressure for lowest running cost. This is for water cooled condenser based systems. For any water cooled condenser based refrigerant system, the total running cost of a refrigerant system is the sum of costs of compressor power and the cost of water, and compressor power increases as condensing pressure increases. Okay. This we have seen in the earlier lectures, and for a given water inlet temperature, cost of water and the water flow rate etc. reduces as condensing temperature or condensing pressure increases. Okay. So, this implies a possibility of optimizing the condenser pressure for minimum running cost. Okay. Let me show a typical picture. This is, for example, I have plotted the cost versus condensing pressure. Okay. So, you find that as the condensing pressure increases, running cost of compressor increases. At the same time, running cost of the water reduces. Since the total cost, which is nothing but running cost of compressor plus running cost of the water, may show a minimum at a particular condenser pressure. Okay. So, this condenser pressure becomes the optimized optimum condenser pressure for this particular plant. Okay. So, if you know the plant characteristics, you can plot these curves and you can find out what is the optimum condenser pressure at which the total cost is minimum. Okay. So, with this I conclude this lecture. In this lecture, expressions for overall heat transfer coefficient are presented, expressions for various heat transfer areas in plate fin type condenser are presented, typical correlations for heat transfer coefficients on air side, water side and during condensation are presented, and effects of non-condensable gases and optimum condenser pressure are briefly discussed. So, in the next lecture I will work out problems on the design of air cooled as well as water cooled condensers. Thank you. Two problems on condensers, then I will introduce refrigerant evaporators. So, the specific objectives of this particular lecture are to present worked out examples for thermal design of water cooled and air cooled condensers, introduce evaporators, present classification of evaporators, describe salient features of some of the important types of evaporators. And at the end of the lesson, you should be able to carry out thermal design of air cooled and water cooled condensers using suitable correlations and formula, classify refrigerant evaporators based on various criteria, describe important features of some of the important types of evaporators. So, let me begin with a worked out example. This is an example on shell and tube condenser, and the problem statement is like this. You have to find the length of tubes in a 2-pass 10 ton capacity shell and tube R22 based water cooled condenser with 52 tubes arranged in 13 columns. The heat rejection ratio is given as 1.2747. The condensing temperature is 45 degrees centigrade. Water inlet and outlet temperatures are 30 degrees centigrade and 35 degrees centigrade respectively. The tube outer and inner diameters are 14 and 16 mm respectively. So, the problem must be clear to you. It is an R22 based condenser, water cooled condenser. It has 52 tubes and 13 columns. 52 tubes are arranged in 13 columns, and the other data is as per the problem. So, now let us look at how to solve the problem. So, this is the schematic. In fact, I have last class I have shown this schematic of a 2-pass shell and tube type of a condenser, and as I have explained to you, here refrigerant is there on the shell side. Okay, you can see that refrigerant is entering at the top and it condenses as it comes in contact with the tubes, and the liquid refrigerant goes out from the bottom, and water enters from the bottom like this. Coolant is nothing but the water, and it flows through these tubes. Since it is a 2-pass, the same water again will flow through the condenser tubes. Okay, so it comes here and again it goes back to the condenser tube. That is why you call it as a 2-pass condenser. That means the water makes 2 passes as it flows through the condenser. And in the problem it is mentioned that there are 52 tubes, okay, and they are arranged in 13 columns. Now, the first thing we have to do is we have to find out the properties of R22 and water, because we have to evaluate the heat transfer coefficients and all. So, these are the properties at average temperatures. For water, viscosity is given as 7.73 into 10 to the power of minus 4 kg per meter second. Thermal conductivity is given as 0.617 watt per meter Kelvin, and density is 995 kg per meter cube. Specific heat of water is given as 4.19 kilojoule per kg K, and Prandtl number is given as 5.25. PR is Prandtl number. And for R22, the average properties are viscosity is 1.8 into 10 to the power of minus 4 kg per meter second. Thermal conductivity Kf is 0.0779 watt per meter Kelvin, and density is 1118.9 kg per meter cube, and latent heat.